This Zoom session is being brought to you by the Fractal Globe Snow Ring B. All right, for today, we cover vectors. I have to say this has only a little bit of trigonometry. This section is mostly about what's called linear algebra. So we proceed anyhow. A vector. It's a displacement between points. Think of it as a move from here, the initial point, to here, the terminal point. It's usually denoted by this little arrow. So, okay. And because it's a displacement, it's very useful in physics. Displacements are vectors, so are velocities, so are accelerations, so are forces. So vectors are all over physics and engineering, etc. Excuse me. All right. Now, two vectors are equal if they have the same length and direction. Here are two vectors pointing in the same direction, but different lengths, so they're not equal. Here are two vectors of the same length, but in different directions, so they're not equal. Here are all a bunch of vectors, all pointing in the same direction, all the same length, so they're considered equal. I mean, approximately given my handwriting. Although their initial points and terminal points are all different, so they are equal vectors in different places. So, given a vector in a plane, it'll have a direction along the x-axis and a certain amount of displacement along the y-axis, a by b, and therefore we denote the vector bracket a comma b end bracket. A is the x coordinate of the vector, b is the y coordinate of the vector. Like points, only they're considered as motions rather than places in space. Given a vector between 2 points x1, y1 to x2, y2, the displacement along the x direction is terminal value minus initial value, x2 minus x1. The displacement along the y value along the y-axis is y2 minus y1. So v equals x2 minus x1 by y2 minus y1. This is the value of a vector pointing between 2 points. So we have a vector with a by b, then we'll denote its length by this double bracket around it, sort of like an absolute value sign. And in keeping with the Pythagorean theorem, we say that length of v is a squared. Length of v is the square root of a squared plus b squared, the usual Pythagorean definition. Now, these vectors are somewhat like numbers, a little bit. You can add them, subtract them, and to some extent you can multiply them. There's multiplying by scalars, and next time we'll talk about dot products. And much later on, we'll talk about cross products. Okay, the idea is this. There's two definitions of adding vectors. There's an algebraic definition, and there's a geometric definition. The algebraic definition is just to add components. A by B by big A by big B plus big A by big B. You add the x values, a plus big A by, then you add the y values, little b plus big B. So you add the components in parallel. It's just two additions at once. But another way to look at them is in terms of something called the parallelogram law. If this is a vector v, this one say, and this is a vector w, this one say, then we line up their initial points, and we draw this parallelogram like this. So, okay, at the tip of v, we put the base of the initial point of w like this. At the tip of w, we put the initial point of v like this. And this forms a parallelogram, and its diagonal is a sum, u plus v. This turns out to be the same as this. So there's two ways of looking at the same thing. Then there's, here I'm calling it rescaling vector. It's basically, or multiplying by a scalar, by a number. The algebraic definition is that a number times a by b is ka by kb. You multiply each component by k in parallel, just like here we add components in parallel. And its geometric definition looks like this. If this is a vector v, then 2v is in the same direction but twice as long. A half v is in the same direction, half as long, and minus v is in the opposite direction, same length. And so it goes for any k times v. It'll be multiple, if its k is positive, then it's in the same direction, k times as long, and if it's negative, then it's the opposite direction, k times as long. Oh, in particular, 0v, which would be 0 by 0, is a vector which doesn't move at all. It's a point. Now, this looks a lot like ordinary addition, and it acts like ordinary addition in many ways. For example, u plus v is v plus u. It's commutative. It's associative. U plus v plus w is u plus v plus w. It is 0 for an identity. U plus 0 equals u, where u is a 0 vector, components are 0 by 0. A vector plus the one opposite adds to the 0 vector. Then we have various kinds of associativity and distribution. K times u plus v is ku plus kv. So a scalar multiplication distributes over vector addition. K plus h times u is ku plus hu. So scalar multiplication of a vector distributes over a sum of scalars. And then here's a kind of associativity. K times hu is kh times u. So it obeys a lot of same laws, and so you can do a lot of the same algebra and equations with it. Now, here are two special vectors, 1 by 0 and 0 by 1. 1 by 0 is in the unit length in the x direction. 0 by 1 has length 1 in the y direction. This one is called the vector I. This one is called the vector j. If you use these definitions and these definitions of adding and multiplying vectors, then the vector a by b is the same as ai plus bj. So there are two ways of looking at the same thing. Now, finally, get to some trigonometry. If we have a vector with a given length, absolute value v, and it's tilted at an angle theta relative to the positive x-axis, then we'll get by a rule like we found before for polar coordinates for complex numbers, that vector v is the length of the v times cos v by sine v. This cos v by sine v, a lot like cos theta by sine theta, my apologies. This is a lot like cis theta for complex numbers. It's a unit vector in the v direction, which is the length of v divided by its length. Take v and divide it by its length, you get this. So we have some examples. Here we have a vector with length 14 at an angle of 120 from the x-axis, so it'd be winding up in the second quadrant. What's vector v? Well, it's length times cos theta by sine theta. That's 14, the length, times cos 120 by sine 120. Bit of elementary algebra, cos 120 is minus a half, sine 120 is root 3 over 2, multiplied by 14. 14 times minus a half is negative 7. 14 times root 3 halves is 7 root 3. So that's the answer. Also denoted minus 7i plus 7 root 3j. Or here's some other examples. Here's a vector with initial point -2 by -1 and terminal point 6 by -2. What is the vector? All right, so we just subtract components. 6 minus -2 here, -2 minus 1 here, and a bit of arithmetic is 8 by -1. That's the vector. Here's the length. Here we ask, what's the length of the vector 3i plus 4j? Length of 3 by -4. It's the square root of sum of squares components. Square root of sum of 3 squared plus -4 squared. And okay, that's root of 9 plus 16 is root 25 is 5. The 3, 4, 5 triangle shows up again. What's the length of the vector I minus j? Well, let's see. I is 1 by 0, minus j is 0 by -1. They add up to 1 by -1. The length of 1 by -1 is root of 1 squared plus -1 squared. That's root 1 plus 1. That's the square root of 2. That's 39. Now for this one, we have several questions. We're given a vector v, 3 by -5, and a vector w, -2 by 3. And let's find out what's 2u plus 3v, what's the length of u minus v, that's a v minus w, my apologies, and what's the length of v minus the length of w. Slightly different questions. Here we subtract and take a length. Here we take lengths and subtract. 2u plus 3v. Well, so let's look at this again. Here's a v. 3 by -5 W is negative 2 by 3. 2v plus 3w is twice 3 by negative 5 plus 3 times negative 2 by 3. Twice negative 3 by negative 5 is 2 times 3 is 6, by 2 times negative 5 is negative 10. 6 by negative 10. 3 times negative 2 by 3, 3 times negative 2 is negative 6, 3 times 3 is 9. Okay. 6 by negative 10 plus negative 6 by 9. Okay, we add components. X component is 6 plus negative 6. Y component is negative 10 plus 9. This is 0 by negative 1, otherwise known as negative j. So here we have it. Length of u minus w, v minus w. I've been doing this so much, I gotta get hot for that. Length of v minus w. Well, 3 by negative 5 minus negative 2 by 3. What's its length? Well, 3 minus negative 2 for the first component, negative 5 minus 3 for the second component. That's 5 by negative 8. The length of that is square root of 5 squared plus negative 8 squared. That's square root of 25 plus 64, which is a square root of 89, and we're done. Now, here we have length of v minus length of w. Length of 3 by negative 5 minus length of negative 2 by 3. Well, length of 3 by negative 5 is the square root of 3 squared plus negative 5 squared, which is root 9 plus 25 is root 34. Length of the negative 2 by 3 is negative 2 squared plus 3 squared is 4 plus 9 is root 13. So the end result is root 34 minus root 13, which, as you might guess, is quite different from root 89. So it matters which you do first, the subtract or the absolute value. Here we have some ones which finally do a little bit of trig. Given a vector, length 25, at an angle 330, what are its components? Well, it'll be 25 times cos 330 by sine 330. Cosine 330 is root 3 over 2. Sine 330 is minus a half. All that times 25 is 25 root 3 over 2 by negative 25 over 2. That ends that. Now here we have a somewhat more difficult one because it's going to combine some trigonometry with some linear algebra with solving a linear system. Not trivial. Here's what's going on. Here's a 1,000-pound weight hanging from 2 cables. It doesn't sound like very good engineering, but let's assume that anyhow. And this cable is at an angle of 25 downwards. This cable is at an angle of 40 degrees downwards. What are the 2 forces on the cables? Now, okay, here we have to use a bit of engineering. The idea is called equilibrium. This 1,000-pound weight has a force of 0 by negative 1,000. This one here is force 1, here's force 2 at an angle of 25 degrees, at an angle of 40 degrees. Okay, and 25 is supplementary to 155. Okay, now here's the trick. If this weight is not moving, then it's at equilibrium, which means that all forces on it add to 0. So F1 plus F2 plus 0 by negative 1,000 equals 0. That's static equilibrium. So, okay, we need to know the components of F1 and F2. F1, its force is F1 times cosine 155. Remember, we have to have theta is the angle from the positive x-axis. Here's 25 degrees from the negative x-axis. That's the same thing as 155 degrees from the positive x-axis. So F1, that force F1 is length F1 cos 155 by F1 sine 155. F2, well, F2 times cosine of 40 degrees by F2 sine of 40 degrees. So these 2 forces plus 0 by negative 1,000 adds to 0 by 0. So F1 cos 155 plus F2 cos 40 by F1 sine 155 plus F2 sine 40 minus 1,000. All that sums up to 0 by 0. Now, okay, vectors are equal if their components are equal. So F1 cos 155 plus F2 cos 40 is 0. F1 sine 155 plus F2 sine 40, well, minus 1,000 equals 0, so these add up to plus 1,000. This is a 2 by 2 system. It's a linear algebra system. I will not bore you with the details of calculating it. It's pretty routine. And we get that F1 is 845.2 pounds, and F2 is surprisingly 1,000 pounds, just as much force along here as along here. So I think that this cable here is entirely wasted. But never mind that. Those are the numbers. And I do believe you do have a problem like that, perhaps extra credit in the problem set. Okay. I think that should do it for now.